Hello, everyone, and welcome to this model on content routing. This is the agenda that we're going to follow throughout the presentation. We're going to start with a brief introduction to understand the differences between location addressing and content addressing from a content routing point of view. And we're going to see the challenges of content routing in peer-to-peer networks. We're going to jump into explaining afterwards the content routing architecture in the IPFS network, and we're gonna describe the different implementations that we have currently in place in the IPFS network to perform content routing, which are mainly a DHT-based content routing approach and a gossip-based content routing approach. So the main difference between location addressing and content addressing is in the way we search and fetch content from the network. In a location addressing based network, what we're going to do is try to find content through its specific location. So we usually send a request to a centrally governed system like the DNS system requesting the specific file, and we will get back the specific location where the file is stored so that we can go directly to this server and download the file. This is not the case for content addressing. In content addressing, what we do is to request content through its unique ID. So if we want to download a file, we send a request to the network for this unique ID. And what we do is send this request and we will start getting responses from the different peers saying if they're storing or not that content. At one point, we may choose one of these peers and request, once we know where the content is stored, the download of the specific content. So this is how content addressable networks work. In peer-to-peer networks, we have a lot of challenges for content routing. And the main reason for these challenges is the lack of a central entity that aids us for the orchestration of the storage and discovery of content. We saw in the location addressable network example that we have a centrally governed system that we can go and query where the content is stored, the specific location of the content, and how to dial the server that stores that content. This is not the case for peer-to-peer networks because there is no central entity orchestrating the storage and discovery of content. But not only this, there is no central directory to find how to reach every peer in the network. And to add to this, in peer-to-peer networks, we have high node churn. So we will have nodes that are continuously joining and leaving the network. And when the network is large, we would have thousands of peers. So we have to orchestrate all of this content routing with thousands of peers and millions of content. So we see that all of these challenges of content routing in peer-to-peer networks affect the discovery of peers in the network, finding the peers that are storing specific content in the network, contacting these peers, so finding ways in which we can contact these peers, and doing all of this using protocols that perform this task in a scalable way. And this is mainly what we're going to be discussing throughout this model. And we're going to start discussing the content routing architecture in the IPFS network. And this content routing architecture in IPFS is implemented through a content routing interface. This content routing interface implements different types of protocols and exposes three main operations: a provide operation to make content available for other peers in the network, a resolve operation that is used to find peers that may be storing content in the network, and the fetch operation that is used to actually request the download of the content. According to the specific protocol that implements this interface, we may need additional schemes to find ways in which we can contact the peers that are storing that content. And these schemes, we call them peer routing. This is the case, for instance, for the DHT. In the DHT, we use the DHT as a directory in order to find all of the contents that is stored in the network, as we're going to see in a moment. But we also use the DHT to store information about how to contact the different peers and the different peers that are connected to the network. All of the protocols that implement this content routing interface need to follow the following design goals. First, these protocols should be reliable. So they should give us a way of finding any content that is stored in the network in a reliable way. Also, they should be scalable and fast. So the performance of the queries and operation over this protocol are not affected by the size of the network. And finally, they should be resistant to node churn and Sybil attack, because as we've seen, peer-to-peer networks, in peer-to-peer networks, nodes may be joining and leaving, and they may generate new identities. And our protocol should, content routing protocol should accommodate for this. In IPFS, we have two main approaches in place to implement the content routing interface. First, the main one, that is a DHT-based approach, which is implemented through an adaptation of the Kademlia DHT. And then we have different gossip-based approaches that we can use also for content routing, like the implementation of different PubSub algorithms, and Bitswap. Bitswap is the main content exchange protocol in IPFS, and it does a gossip-based content routing approach to find content in parallel to the DHT. And we'll see in further modules in depth how this Bitswap protocol works. Before we start explaining the content routing interface and the content routing implementation in depth, let's make a quick detour to explain what is a peer in the IPFS network. A peer, in the end, is a device that is connected to the network and has a unique ID in the peer-to-peer network namespace. Peers usually provide services to other peers and can access the services of other peers. So they will be running protocols that can be used to interact with other peers. Peers should be discoverable, and also they should be routable and reachable. For the discovery part, we usually use the DHT. So we'll see in a moment that the information, in order to know what peers are connected to the network and how to contact them, we will store this information in the DHT. And also they should be reachable. So, and for this, we use what we call a multi-address. A multi-address in the end is a list of addresses for different protocols that we can use to contact specific peers in the network. When a peer interacts with other peers in the network, they usually they use encrypted communication channels. And for this, when a peer joins the network, it generates a cryptographic key pair. And this cryptographic key pair has two main purposes. First, through the public key of this key pair, it is inferred the unique ID in the peer-to-peer network namespace for the peer. And on the other hand, this cryptographic key pair is used to establish the encrypted connection with other peers when we interact with them. So let's jump now to explain how the DHT-based routing works in IPFS. As I've advanced, IPFS uses an adaptation of the Kademlia DHT implemented in the lib peer-to-peer package. A DHT in the end provides a two-column table, a key value store, that is maintained by multiple peers in the network. Each row is stored by a different peer, and the way in which we decide and we know what peer is responsible for storing a certain key is through the ID of the peer and the specific key of the information that wants to be stored. So if, for instance, in order to know if I'm the one responsible for storing a specific key, what I have to do is to take my peer ID, take the key, and see how close I am to that key. Because in this case, my peer ID will be responsible for storing keys that are close to it. So we'll see in a moment how this closeness metric is computed in the Kademlia DHT. And in a DHT, we can store any kind of information. In IPFS, the information that we store in the DHT is the following. We store peer routing information. So we will store for the key is related with the peer ID, and in the value, we will store this multi-address, so this list of addresses that we can use to contact other peers. And this is an example of one type of information that we store in the DHT in IPFS. So peer routing information, how to contact peers. Then we also store content routing and content discovery information. So in the key, we will put in a key related to the content identifier of the, for a specific CID, we will store in that key information about the list of peers that are storing that specific content. And also in the DHT, we store information related to IPNS records, but we will explain in depth IPNS record when we talk in following models about mutable content. So the IPFS DHT is an adaptation of the Kademlia DHT that uses a 256-bit address space. As I've said in the previous slide, we can store any kind of information, but we only have a 256-bit address to store this information. And the way in which we compute the key in which we have to store this information is done through a SHA-256. So if we want to store information or peer routing information about a peer, what we would do is take the ID of that peer to the SHA-256, and in this way, know the key in which we have to store that information. And the same for the content discovery information. We get the CID, we will see in a moment, we SHA-256 that CID, and that way we know the key in which we have to store the provider record. That this provider record we'll see is this pointer that specifies the peer addresses that are storing in the network the specific content for that CID. And the way in which the Kademlia DHT computes distance is through an XOR. So if we want to know how close we are to a key, we can get our peer ID and XOR it with that key. And through this, if we just do the XOR between the peer ID and the key, we're able to see how near or how far we are to that key. And the Kademlia DHT uses a binary tree, a tree-based routing in order to store routing information. So we store all of the routing information in a tree structure as the one that we see in the slide, and we divide the information into what we call different buckets, and these buckets are structured using this binary tree. These buckets, buckets are represented as circles in this tree, and in this bucket what we have is a list of peers that share the same prefix. So whenever we want to find, we start adding all of these peers that we've interacted with and that share the same prefix in these K buckets. And if we want to find content in the network, for instance, for a key that has a prefix 101, what we do first is go to our routing table to this tree, traverse the tree until we go to the bucket that is in the 101, get a list of peers from the bucket and start parallel request, asynchronous request to all of them to see if they are storing the content for the DHT that we are looking for. If they are storing the content, they will share it with me right away. And if this is not the case, well, they will answer is with a list of the closest peers that they have to the key I'm looking for. And in this way, I will be able to what we call walk the DHT and reach closer and closer to the key until we find a peer that is storing the value for the key that we're looking for. And this is how the Kademlia DHT implementation works. As I've said, the content routing interface in IPFS has three main operations. We're going to start talking about the provide operation, which is the one that we use to announce content in the network. Content in the IPFS network is not replicated or uploaded to any external server. So it stays local to the user's device of the one that is providing the content. Whenever we want to provide content for a specific CID, what we need to do is to put a pointer to our machine for that CID, to our machine in the DHT. And the way in which we do this is first, we need to look up the K closest peers to the key for that CID. So we take the CID, we do the SHA-256 as we saw to get the key for that CID, and we put this pointer that we call provider record for that CID pointing to my machine, to my peer ID, because it's the one that is storing that content. The reason why we put this provider record in 20 peers is to accommodate node churn, something that we know that we have in the network. So we have several mechanisms in order to accommodate for this node churn that we have in the network. First, provider records expire. And the reason why provider records expire is because at one point I may disappear from the network and I may be the only one storing content. And if we didn't add this expiration to provider records, we would have pointers in the DHT that point to content that is not stored in the network anymore. Because if I'm the only one storing the content in the network and I leave, there's no way of reaching that content anymore. So this is the reason why provider records expire every 24 hours. And also there needs to be a republication of provider records every 12 hours. The reasons for this is that not only I can leave as the provider of the content, the network, but also the K peers, that in this case, the 20 peers where I put the provider record and this pointer may also disappear. So in order to accommodate for these nodes leaving the network, I republish every 12 hours. So providers need to republish every 12 hours this pointer, so that even if some of these nodes peers storing this pointer, this provider record to me disappear, I have a way of keeping fresh the pointers to the content that I'm providing. And also peers that are requesting content from the network can become temporary providers. If at one point another peer tries to get the content that I'm providing, it will become itself a temporary provider. If it wants to become, instead of a temporary provider for the content, a permanent provider, it would have to do something that we call pinning the content. So when we get content from the network, we become temporary providers, but we become temporary providers until the content is garbage collected from our peer. But if we pin, we also add to the provider records our own peer ID, so that we are just another peer in the list of peers. And when we pin content, we will be republishing these provider records so that everyone knows that I'm also a permanent provider in the network. And finally, I mean, we may be interacting with the network and storing a lot of content, and the garbage collection in our peer is triggered after we have reached the 90% of the IPFS peer data store that by default is 1 gig, the data store, the default data store for an IPFS peer. And this garbage collection is done every hour. So every hour, what we would do is that content that we are not pinning and for which we are not permanent providers will be removed from our data store in an orderly basis, in order not to have a lot of garbage and be constantly providing content that we are not using. And this is for announcing content in the network. In the case of the resolve operation, finding, which means finding the nodes that are storing the content we're interested in, we used a similar approach to the one that we saw for providing content. The first thing that we do is take the CID of the content that we're looking for, and we do the SHA-256 to know the key in the DHT where the content is stored. We perform a walk in the DHT in order to find the provider record, in order to find the K closest peers that are storing the provider record, the pointer to the peer ID that is storing the content. So we perform the walk to the DHT, we get the provider record, and we get a list of peers that are storing that specific content. From here, we may have the multi-address in order to contact these peers, or we may not have it. If we don't have a way of contacting these peers that are storing the content, what we have to do is an additional walk in the DHT in order to find the multi-address, so the list of addresses that we can use to contact this peer. So that's why we say that resolving content in the IPFS network is a multi-round iterative lookup, because we have to do a first walk in the DHT in order to find the provider record, so the pointer to where the content is stored. And we need to do an additional walk in the case that we don't have information about how to contact the peer that is storing that content. And something that is worth noting also about the IPFS DHT is that with recent upgrades in the protocol, we have two DHTs, a public DHT and a private DHT. And the reason why this is this way is because of performance. Because when we had a single DHT with public and private nodes, what happened is that some of the records and some of the information stored by peers was stored in nodes that weren't reachable from a public network, which means that whenever we started working the DHT, we found providers in a provider record, and the moment we wanted to contact them, they were behind an ad, or they weren't reachable. So we had to do several walks, losing a lot of time to triumph until we found a peer that is publicly reachable. So in order to avoid this, we have a public DHT and a private DHT for a peer. The public DHT only includes publicly reachable peers, and the private DHT includes peers belonging to the same private network. So when we do a walk in the DHT, we do two parallel walks, a walk for the public DHT where we know that we are going to target publicly reachable peers, and then a private walk in the private DHT for the case in which the content may be stored in somewhere in our private network. And finally, the DHT-based content routing approach has its pros and cons. It is fault tolerant and resistant to churn. The DHT find the content in peers with 100% of probability as long as they are reachable. So if we announce content through the DHT, we know that as long as the content is still in the network and reachable, we know that with the DHT, we have 100% probability that doing a walk, we will be able to find that content. And also the DHT ensures freshness of the routing information. However, there is a trade-off, because the problem is that the DHT can be slow in networks with large number of peers, because doing a walk in the DHT when there are a lot of nodes in the network may be slow. So performing operations on large scale networks on the DHT may be slow. And also DHT proximity is not the same as spatial proximity, because the DHT builds an overlay network over the underlying transport network. And when we say that we're one step closer in the DHT or just one, we're close to a peer, this doesn't mean that we are close in the underlying transport protocol or the underlying network. So when we just do one step in the DHT and we're going to the closest node, this may mean that we're doing lots of jumps and we're going to a really far away node in the underlying network, harming performance. So that is why there's now a lot of research in which we are trying to make DHT proximity the same as spatial proximity in some ways, so that close to the DHT is also means close spatially to our peer. And finally, to sum up, let's see the default configuration of the DHT-based approach in IPFS. In the Kademlia adaptation of the adaptation of the Kademlia DHT in IPFS, the buckets are of size 20. So the K I've been mentioning is by default in IPFS 20. The alpha, the number of peers that I get from the bucket and send parallel requests to when we do a walk, is 10. So we get 10 peers from the list from our K bucket, and we start in parallel 10 different requests to start the walk. And the beta is the number of successful requests that we wait until we terminate the walk. So we may start a walk, send parallel requests, start the walk, and if 3 of these parallel requests are successful, we terminate the walk as it being successful. And this beta number is 3. And finally, the K bucket refresh interval is of 10 minutes in our routing tables. For the provider records, the republish interval, as I already advanced, is 12 hours. So every 12 hours, we need to republish the provider record to accommodate node churn. And also the provider record expiry is of 24 hours. So provider record stops being valid after 24 hours if there has not been a republish. Finally, garbage collection is triggered every hour when we reach up to a 90% of the size of the total size of the data store of an IPFS node, which for default is configured in 10 gigs. And finally, let's discuss, as the DHT-based routing may have some trade-offs, we use gossip-based routing to complement it. And in IPFS, we have 2 ways in which we can do gossip-based content routing. First, we have bitswap, because bitswap is the content exchange protocol that orchestrates the fetch operation, so the fetching of content from peers. And bitswap does a gossip-based content routing approach by asking its neighbors for some content that the IPFS peer may be looking for the case in which they are also storing that content, so that in parallel of making this DHT request, as we will see in the following model, bitswap also asks its neighbors and uses this gossip-based approach to see if any of the neighbors may be storing that content. And also we can use PubSub protocols to build different swarms where peers may build meshes where they exchange information about different content and about how to reach content in the network. But as I've said, IPFS implements a content routing interface that can implement any kind of protocol. So we would be able to use any kind of external subsystem that implements this content routing interface in order to find content in the network. We could use a BitTorrent tracker, or we could use a centrally governed system as DNS. And to wrap up the model, let's see briefly how the content discovery, and let's summarize how content discovery is in IPFS. Whenever we want to find content in the IPFS network, the first thing that we usually do is get a CID out of bound. The same way we get a URL to find a website, we get a CID in IPFS to get some content. And the first content routing protocol that comes into place in IPFS is the gossip-based content routing, because bitswap, what it does is ask its neighbors to see if any of them has the content for that specific CID. If this is not the case, in parallel, bitswap will start a walk in the DHT in order to find providers for that content. So first we do a gossip-based content routing where we ask our neighbors, and then we perform the work in the DHT. And the work in the DHT is done in the following way. First, what we do is we try to find the provider record. So we try to find this list of peers that may be storing the content that I'm interested in. For this, we perform a work in the DHT to find the provider record. And when we get this provider record, what we do is check the list of peers and see if I have the multi-address in order to contact any of these peers that may be storing the content. If this is not the case, what we need to do is an additional work in the DHT in order to find the multi-address of the provider. So the ways in which I can contact the peer that is storing the content for this specific CID. I find this content, I establish a connection with that peer, and I fetch the content from it. Again, in following models, we will see in depth how this is done through BitSwap. And also, when I get content from the network, I cache this content and I become a temporary provider for that content, so that when other peers ask me for that content, I can also temporarily provide that specific content for that specific CID until it is garbage collected from my peer. And this is briefly how content discovery works in summary in IPFS. And this is all for this content routing model. I hope you've enjoyed. Any questions, suggestions that you have, please let us know, and thank you very much.